The next reaction is sulfonation of benzene. This is to make a sulfonic acid group. All right, sulfonic acid groups are pretty acidic. If you look at it, it looks very similar to sulfuric acid. All right, the structure of sulfuric acid is HOS double bond O double bond O OH. Okay, so you can see that this part of it is basically that part of it. Instead of having an OH here, you have an aromatic ring. So these are fairly acidic. So here's a really good way to make a very, very acidic compound. These sulfonic acids aren't really found that often in nature, but they are found a lot in a lot of the medications we take. Sometimes you have to make it fairly acidic so that it ionizes in water. All right, this compound will ionize in our stomachs. It helps it being absorbed into the body. A few things like this. Also creates a lot of hydrogen bonding. As you know, our bodies are basically this huge, gigantic network of hydrogen bonding. So these compounds, once they enter inside of whatever enzyme or protein or whatever it has to get into, it's going to have to make a tremendous amount of hydrogen bonding. So that's where these types of compounds are found. And it basically uses sulfur trioxide, SO3. It adds it on there, and then it gets protonated by the acid. All right. So the SO3 is electrophile, you know, this isn't really something we really got to know, but it's a 7% mixture of SO3 and H2SO4. It's referred to fuming sulfuric acid. So it's usually very concentrated sulfuric acid. SO3, only a small amount of it is actually soluble in sulfuric acid. That's why it's fuming. It actually fumes out of it. Okay. So here's what sulfur trioxide looks like. It's a very strong electrophile. So again, you can read the slide. There's 3 sulfonyl bond drawings because of the resonance. All right, the electron density. So yeah, the electron density is away from the sulfur atom. Okay, so the mechanism: pi bond attacks the sulfur trioxide, forming the sigma complex. You can do the resonance. We didn't draw it here because you already know it already. And then the sulfonic acid, or the bisulfate ion, plucks off the hydrogen, reforming aromatic compound, putting the sulfonic acid, which then eventually gets protonated by the sulfuric acid. Okay, and this is exactly what I just said. Now, one of the things that you can do with the sulfonic acid is you can actually remove the sulfonic acid. Why would you want to do that? There are reasons we'll talk about a little bit later, but you can do a desulfonation. This is a reversible reaction, so by heating it up in acid, you can take off the sulfonic acid. Okay, so desulfonation. Here's the mechanism. It's the exact reverse, but it's pretty straightforward. Pi bond attacks the proton, gives you the sigma complex. The O minus pops back in and kicks out the electrons between the carbon and sulfur, reform your aromatic compound, and your SO3 bubbles away as a gas. Okay. 17.5 to 17.9. We're going to talk about the nitration of toluene and a few other types of reactions. So now we're going to take a different turn, and up until now we've been talking about mono addition of electrophiles to an aromatic ring, meaning we were just adding one group to a benzene ring. What happens if I already have a group on my benzene ring and I do one of these reactions that we've just learned? Where does the group go? So if I take toluene now and I nitrate it, where does it go? There's 3 places. It's either the ortho position, I can nitrate the ortho position, I can nitrate the meta position, or I can nitrate the para position. Okay? Now, do I get a statistical mixture of all 3? 33% of each one? Well, you can read, apparently I do not. Okay? I get mostly the ortho, okay, then the para, and then a very small amount of the meta. Okay, interesting. All right, now this, if you look at these, this is kind of like a statistical mixture. All right, it's like a 2/3 to 1/3. Okay, which would make sense because I have 2 ortho spots and only 1 para spot. So that makes sense. I would get twice the amount at the ortho positions, okay, and a third at the para. But what's interesting is that I get none at the meta. Okay, now why is this? Why is it that I'm getting ortho-para compounds, but I'm not getting the meta compounds? So there must be something that this group is doing to the ring which allows the nitro group to only go at these positions. Okay, this group, the group that's on the ring, is what's called the directing group. Okay, which makes sense. It directs where the reaction group goes. All right, this basically says, okay, nitro, you can go here in the ortho positions and you can go in the para, but not the meta. So why is this? And this happens with any type of mono substituted aromatic ring. It doesn't have to be a methyl group. We're going to look at all different groups that are substituted on your ring and see how it affects the ring. All right. So this is just to tell you that toluene reacts 25 times more faster than benzene. So this methyl group obviously is what's called an activating group. It activates your ring even more. So there you go. Methyl group is an activator. The product mix contains mostly ortho and para, not really much of the meta. Let's just assume it's 0% meta. So now we're going to see why. Okay? And the only way you can determine why is always by looking at the mechanism in the intermediates. There's got to be something stabilizing about the intermediates. So the pi bond attacks, okay, and let's say that the nitro goes at the ortho position right here. Okay, so you see that the nitro is on the ortho position. We'll put an O there for ortho. Okay, down here it's doing the same thing, it's attacking, but this time the nitro is going to go in the para position. The para, so ortho para. There are two types of directors. There's an ortho para director, and then there's a meta director. It's not like I have an ortho director and then I have a para director and then a meta. It's either ortho para or meta. Okay, those are the two choices. So here are the intermediates. There are 3 intermediates, and they're highlighting the green ones because that's the important one. Notice that when you look at the sigma complex at the resin structures, one of them is a tertiary carbocation. Notice, because we always form carbocations. One of them is tertiary. We've learned that tertiary is the most stable. Okay, the other 2 are secondaries. When you go para, same thing. You get 2 secondaries and you get a tertiary. Okay? Well, what happens if you go meta? Well, let's see what it says. Ortho and para attacks are preferred because their resin structures include 1 tertiary carbocation. Well, what happens in the meta case? In the meta case, I'll come back to that slide. In the meta case, notice, when the nitro attacks, you get, so here's the meta, we'll put M's. Notice your carbocations are, all 3 structures are secondary positions. So in the meta case, they're all secondaries. In the ortho-para case, 2 of them are secondaries, 1 of them is this more favorable tertiary. Okay, so based on the stability of the intermediates, okay, you get mostly ortho-para substitutions. This kind of shows the energy profile of it. Okay, here's, if I were just to take benzene and nitrate it, this is the energy associated with that compound. So if you go across, that's the energy, whatever energy it is. Let's call that energy B for the benzene. Okay, the meta is a little bit more stabilizing. It has to do with the methyl group. Okay, but remember, you get all secondary carbocations. That energy is right there. But with the ortho-para, because you get the tertiaries, that brings it down much more in energy. So your activation energy for here is the smallest activation energy. And we've learned the smaller the activation energy, the faster it's going to go that way. Okay? So this kind of diagram kind of shows that. It explains because of the tertiary, it's more stabilizing, so you get more of the ortho-para product. Okay, now it doesn't have to be a methyl group, all right? It could be any type of sp3 hybridized alkyl group. Okay, sp3 alkyl group. Okay, so it could be an ethyl group, an isopropyl group, a tert-butyl group, a cyclohexyl, whatever you want. Okay, so when substitution occurs at the meta position, the positive charge is not delocalized onto the tertiary, and the methyl group has a smaller effect on the stability of the sigma complex. Okay, so this goes a little bit further into it. So we saw last slide that if you have a methyl group here, you get mostly at the ortho because of the statistical mixture. But notice, in this case, it's the exact opposite. You get more of the para and less of the ortho. So why is that? Why, if this group is bigger? It kind of should make sense. The bigger this group, the more it blocks the ortho position. Remember, this thing is swinging around. Okay, so if I just have a methyl is a small group, I'll get more of it at the ortho and less of the para. As this thing gets bigger, all right, I get more and more of it at the para. So imagine if this was a tert-butyl, all right? Tert-butyl, gigantic group here. How much ortho do you think I would get? Probably very, very little. I'd probably get mostly para, okay? Obviously, you can see meta, virtually none, okay? So alkyl groups are activating groups. They activate the ring at the ortho and the para groups. This effect is called the inductive effect. We've learned what that means. It's basically pumping in electrons into the ring. Okay. Now, what happens if you have an oxygen here instead of a carbon? Okay. Now, remember, there are lone pairs on this oxygen. Okay. What happens is this is also an activating group. In fact, it's 10,000 times more activating than benzene, 400 times more activating than toluene. All right? So obviously these lone pairs are activating it, and you'll notice the same exact thing. You get mostly ortho-para. Okay? So oxygen is an ortho-para director. Oxygen is ortho-para director. Okay, and what we're looking at is the group that's directly attached to the aromatic ring. Now, notice we get more of it at the para. This would make sense because you got, relatively large group. As this gets bigger, it's going to block more and more of those spots. Okay. On the next video, we're going to talk about why.